AC voltage applied to a series LCR circuit. The following figure shows a series LCR circuit connected to an AC source. As usual, we take the voltage of the source to be V equals Vm sin omega t. If Q is the charge on the capacitor and I the current, at time t we have, from Kirchhoff's loop rule, L di by dt plus IR plus Q by C equals V. The instantaneous current I and its phase relationship to the applied alternating voltage V can be determined by two methods. First method, we use the technique of phasors. Second method, analytical solution, we solve the following equation analytically to obtain the time dependence of I. Click on the buttons to know in detail about the methods. On the left hand side, you can see the graph showing the relation between the phasors VL, VR, VC, and on the right hand side, the relation between VL, VR and VL plus VC is shown. Since phasor I is always parallel to phasor VR, the phase angle phi is the angle between VR and V and can be determined from the shown figure. We have tan phi equals VCM minus VIM divided by VRM. Now this can be written as tan phi equals XC minus XL divided by R. Click on the button to see both these equations graphically. Phasor diagram. You can see the graph of voltage and current versus omega t for a series LCR circuit where XC is greater than XL. Click on the play button to see the phasor diagram for the circuit. From this circuit, we see that the resistor, inductor and capacitor are in series. Therefore, the AC current in each element is the same at any time, having the same amplitude and phase. Let it be I equals Im sin omega t plus phi, where phi is the phase difference between the voltage across the source and the current in the circuit. On the basis of what we have learnt in the previous sections, we shall construct a phasor diagram for the present case. Analytical solution. The voltage equation for the circuit is as shown. We know that I equals dq by dt. Therefore, on further differentiation, we get di by dt equals d2q by dt2. Thus, in terms of q, the voltage equation becomes as shown. Now this is like the equation for a forced damped oscillator. Let us assume a solution. Q equals Qm sin omega t plus theta, so that dq by dt and d2q by dt2 have the values as shown. Substituting these values in equation 1, we get the following outcome. Here, we have used the relations xc equals 1 by omega c and xi equals omega L. Multiplying and dividing equation 2 by z, which is root over r square plus xc minus xl whole square, we get the following. Now let r by z equals cos phi and xc minus xl by z equals sin phi, so that phi equals tan inverse xc minus xl by r. Making these substitution in equation 3 and simplifying, we get the following. Comparing the two sides of this equation, we see that Vm equals Im into z, where Im equals Qm into omega and theta equals minus pi by 2 plus phi. Therefore, the current in the circuit is as shown. Thus, the analytical solution for the amplitude and phase of the current in the circuit agrees with that obtained by the technique of phasors.